everyone. Here Saina Chaitanya, Assistant Professor in Department of ECE, RGKT Basar. For today, we aim to learn different geometrical models. So in the yesterday class, we came to know what is the image formation process and what are the drawbacks that I am having in the first case and how the drawbacks are overcome by keeping the barrier in the second case. So this barrier is having a small opening or a hole. This hole we call it as an aperture through which the light rays will strike the image plane. Okay, now the three most important geometrical camera models are here: pinhole camera model, perspective projection camera model, as well as the orthographic projection camera model. So let us see and discuss one by one. Now coming to the first camera model, that is pinhole camera model. So this structure is very much similar to a human eye, where we are having an opening. You can see here there is a pinhole here. So this pinhole or nothing but an aperture. It is nothing but a pupil of our human eye. Okay. So in case of a camera, we have here a sensor plane, but in the case of a human eye, we will be having a retina. The terrific character of a retina here is the retina having two types of photoreceptors in retina. Those are rods and cones. These rods are responsible for monochromatic vision and the cones will be responsible for the color vision. Okay, but coming to here, what is happening? I am having a 3D object here. So this 3D object is getting projected on this image plane through this process. That means through this pinhole, I am able to penetrate the light rays through the pinhole, and these light rays which carry the information of this 3D object will be striking, and where we can see the object, inverted object in this 3D structure. Right. Okay. So here the image is inverted. Okay, so as I have already explained you, if I want to get a image which I am viewing it naturally, so there is a software. The software in the camera or the algorithm in the camera will be taking care of it to get the actual image. Okay, so but coming to a human vision perceptions, so where the image is inverted, but the brain can interpret the image, the actual image which is found in our environment. The brain can interpret it in the right way. But for camera, what is the thing here? The software or the processor which is present inside the camera functioning is responsible for getting a actual image, actual object visualization onto the image plane, what we are going to see here. So for a camera, a software can simply flip the image top to down as well as the right to left. So there will be a trick. Okay, I will explain you this trick in the further slide. So the same concept I have also showing you here. So this is my enclosure and this is my pinhole camera. So this is my complete box, right? So this box is having a small hole. This small hole is nothing but it is an aperture. So this is a pinhole, and the distance from this point to this image plane, let me call it is a focal length of the camera. So I will be having my image plane here, so where I can able to see a 2D inverted image. So this is my 3D object that is present in the environment. So before the light rays are penetrating through the pinhole of the camera, there will be a virtual image. So in the virtual image, how the object is appearing in the 3D scene, the same thing can be visualized in the virtual image plane. Okay, so I have said you right that this is my pinhole, and this pinhole is nothing but it is an aperture of your camera. So aperture comparison. So this is nothing but the diaphragm of the camera, this one, and it's the diaphragm. Okay, so the amount of light that falls on the retina determines the size of a pupil. But here diaphragm is controlling the aperture, as how the iris is controlling the pupil of the eye. In the similar manner, the diaphragm will be controlling the aperture here. So this is my aperture, this is my larger aperture, this is my smaller aperture. So larger aperture means, can I say it is nothing but a larger pupil in terms of human visual system? Okay, so in the larger aperture of lens will be letting more light to enter into the camera, but a smaller aperture will result in lesser amount of light to enter into camera. Okay, so I think you have understood a clear difference between a larger aperture as well as the smaller aperture. So in our earlier class discussion, the aperture is expressed in f number or f stop. That means this f stop is inversely proportional to aperture size. So we know that aperture has a direct impact on depth of the field. Okay, so all the things we have discussed in the previous lecture of mine. Okay, so the larger aperture will provide lots of light to enter into the camera, but a smaller aperture will leads only lesser amount of light to enter into the camera. Now the larger aperture will result in the shallow depth of the field, and smaller aperture will be resulting in the more depth of the field here. So let me assume this is my in terms, if I would like to express this in terms of a f number. So let it be, it is of f16, let it be, it is of f 1.4 or 2.2 kind of. So this f16 brings all foreground as well as background objects into the focus. So by seeing this image, this is the object that is present in my 3D environment, and this is my pinhole camera setup. This is my pinhole, and where I am having at the center, this is an aperture will be present at the center of my pinhole camera, and we are going to get an inverted image in the image plane. So when compared to this image, you are having the image in this image plane is bit clearer when compared to the image that is focused on this image plane. Why? Because as I have said you, this pinhole camera is using f16 aperture, which brings all the foreground as well as the background objects in focus, and it gives a bit more clarity in the information. But coming to here, let it be this pinhole camera is carrying an aperture of length f 1.4 or 2.2. So that means what is happening here? So either the foreground or the background objects, either any one among these two will be focused. Okay, that means we cannot get more clarity on the information that is projected in the image plane. So this is what happening here. Okay. Now let me, that means can I finally figure it out that the aperture size here affects the depth of the field, and also it is evident that smaller aperture increases. Here you can see the smaller aperture increases the range in which the object is approximated in focus. Okay, so this is much approximated in focus when compared to this one. So larger aperture corresponds to shallow depth of the field, and smaller aperture here corresponds to larger depth of the field. Okay, so what is the pinhole camera actual concept is? Let me assume in my environment I am having a 3D object. So that means here this star is there, right? This blue color star is nothing but some object in my environment. So definitely it is associated with the coordinates x comma y comma z. So let me represent this star with capital P as a point. So this is my 3D point capital P, and its coordinates are x, y, z, because I am taking it in a matrix form. so which is a 3 cross 1 matrix, because I have taken here transpose. So 3 cross 1 matrix, that is x, y, z. This point P is having these coordinates. This point is projected on to your 2D image plane. Because if I consider this is my pinhole camera enclosure or the box or the setup, this is my object present in the environment. So this object will be visualized in the image plane at this location. Because we, as I have said you, we always get an inverted image in the image plane. So this 3D point P is projected to 2D image point as small p, whose coordinates are x comma y. So x, y transpose, that means it is a 2 cross 1 matrix. Now we know according to the law of similar triangles and symmetricity, we have here, let me consider the height of this point or the height of this object is y units. So it is y units away from your z plane, and also y units away from the z plane, as well as x units away from the z plane, because it is a 3D coordinate system. So in the image what I possess here, I will be having that it is small y units away from the normal plane, as well as small x units away from this reference plane, right? So can I write now, if I consider this one as a small triangle and if I consider this one as some triangle, so according to the law of similar triangles, because it replicates me a similar triangle, right? So small y by small f, y by f, okay, that means height of the object or height of this point in the image plane by focal length is equal to capital Y. What is this capital Y? It is the height of the object in the 3D environment by Z. So this Z indicates me that the distance between the lens of a camera or the pinhole. So of course I have called it as a pinhole. So that means it is nothing but it is a lens of a camera. So the distance between the lens of a camera to your object is represented by Z as a notation. So small y by small f equal to capital Y by capital Z. Similarly, I do also possess one more coordinate in the imaging system, right? That is x. So x by f is also equal to capital X by capital Z. So finally, I would like to figure it out that y is expressed in terms of capital Y by capital Z into small f. And similarly, x is also expressed in terms of capital X by capital Z into small f. So this small f represents here, it is nothing but the focal length of your camera. So focal length, this is the one. The distance between the lens of your camera to your image plane is nothing but the focal length. Okay. So let us see a small problem on the things so far discussed. If the focal length, that means small f, as I have already have here, that is 17 mm. The observer is looking at a tree 15 meters high. So this tree is 15 meters in height, and this observer is at a distance of 100 meters from the tree. Okay, so 100 meters is there. So this is my human eye, and of course here I will be having some inverted image. Find the dimension of the object perceived in the retina. So this is my retina plane, right? So in the retina plane, what I will be having an inverted image. So what is the thing asked here? Find the dimension of the object. So here this is my length of the tree. What will be the length of the tree in the image plane? This is the question that was being asked here. So if I assume h is the height in millimeter of the object in the retinal image, so small h here, so small h is nothing but your height of the image in the retinal plane. So small h by small f, that means h by 17 equal to 15 by 100. So according to this principle, what we have discussed just now. So small y by small f equal to capital Y by capital Z. So the same thing I have shown here. So finally, I am going to get the height of the object in my image plane as h equal to 2.55 mm. So it is always advisable to measure whatever the thing we are dimensioning in the image plane. It is always advisable to go with millimeter dimensions. So the next concept here is the thin lens equation. So what is this thin lens equation? In this thin lens equation, we neglect here the thickness. So here the same thing I have projected. So this will be my lens of a camera, right? Okay. So where the thickness of this lens of a camera, I am assuming it is very negligible, right? First point. And also assuming that the medium is same on both sides of the lens, because if I assume this one as the lens of a camera, the medium that is present here as well as the medium that is present here, the medium is considered as a same. Okay, so the same thing here I have I'm depicting, right? So let me assume a object O is focused on the image plane. Actually the image plane have to come and sit here. Okay, so some minor mistake is there. So the image plane will be here. Okay, so a 3D object in the world is which is present at O location is focused at O dash in the image plane. That means, can I say at O dash is nothing but, according to here this diagram, it is an intersection of three rays. Okay. Now there will be a ray from this O vector through n. So this n is nothing but here nodal point. Okay, or the center of projection. Okay, so there also will be two rays parallel to the optical axis. So what is this optical axis? This will be by optical axis. So there will be two rays which are parallel to optical axis. One will be in front of. So this will be in front of. That means this will be in front of. Okay, and the next one is one will be. So here you can see, right? F, this is one point. Okay, and one will be in front of your lens and one will be behind. So this is the one what you see here. This is the behind the lens. Okay, which passes through the rear or front focal points. That means it is here passing through the front focal point, and this ray will be passing through the back focal point. So this focal point, let me call it as an F dash, and this focal point, let me call it as an F. So this F and F dash, can I assume these are opposite side of the lenses? So this F is in front of the lens, this F dash is behind the lens. So behind the lens we do have the image plane, and in front of the lens we do have the object scene or the object point. Now what is this thin lens equation? Finally, the thin lens equation is giving us the information about the focal length as well as the distance between the lens to actual 3D object as well as the distance between the lens to your image plane. Okay, so that means Z dash here. Okay, let me see the same concept here, how we have got the equation. So the same thing here, focal point, this is my focal point. Okay, so the thin lens equation, this is my lens, this is my height of the object in the environment, this is my height of the object in the image plane. Okay, I am having two focal points, one will be behind the lens and one will be in front of the lens. Okay, so what's happening actually here is, in some cases like we will be having the image plane here itself only, where we are getting the focal point is defined as the distance between the center of the lens to your image plane. But coming to the thin lens equation, it is a bit different. How it will be, we'll see. So this is my height of the object in the 3D environment, h naught, and hi is representing the height of the object in the image plane. So there will be a ray that starts from the object. We call this ray as P ray, and because as I have said you, it is some kind of a convex thin lens. This rays will be bending and it is passing through the focal point F, which is behind the lens, and it is striking the image plane here at this point. There also one ray that passes through the pinhole or the aperture of your lens, and it is striking the image plane here. Alright? Okay, so that means we are having here two rays. Now if this is my h naught, the same dimension is also replicated here, right? If this is h naught means this is also h naught. Okay, and according to your basic mathematics, so if I am having an angle theta, so this theta here I am having means the same angle I also will be having here. Okay, so if small f is the distance between this one as well as this focal point to the lens, if small f is the distance, and if di is the distance between the image plane to your lens of your camera, and d naught is the distance between your lens of your camera to your object. Now this f is nothing but a focal point that is in front of the lens. This f is nothing but it is also a focal point which is present behind the lens. Okay. Now because of the P ray, I am having here an angle theta. Now I am able to find out what will be my tan theta. So tan theta is nothing but it is opposite side by adjacent side. Okay, so what is my opposite side here? This one, h naught. Its dimension is h naught, and the adjacent side will be, it is f. The same thing I have written here. So if the angular displacement is theta here means the same this angular displacement I also will be having here. So can I also write tan theta as hi by f, hi by di minus f, because it is my opposite side, it is my adjacent side. So this opposite side is in negative y-axis. Okay, if I consider this one is in positive y-axis, then definitely it will be in negative y-axis. So minus hi by di minus f. That means this tan theta as well as this tan theta, these two tan thetas are equal means h naught by f is nothing but minus hi by di minus f. Okay, keeping it aside. So if there is a ray, as I have already discussed with you, there are two rays which are passing through the lens and striking the image plane in this manner. Okay, now if there is one more ray, if this is my P ray, and let me call this ray as M ray. So this M ray is passing through the hole of your camera and it is striking your image plane at this point. Okay, that means this P ray and M ray are intersecting at this point, right? So this point indicates me it is the height of the object in the image plane. Now, so there will be an angular displacement or angle associated with this M ray with respect to the center of the projection. So this center of the projection, the angle I am going to call it as an phi. So here if it is phi means definitely the same thing, the same angular displacement I am also going to face here also. That means can I write tan phi equal to h naught by d naught here. Tan phi is nothing but opposite side by adjacent side. Okay, d naught is nothing but it is the distance between your between your object as well as the lens of the camera. So tan phi equal to h naught by d naught. Here also I can able to calculate tan phi. Tan phi equal to hi by di. So as this is in negative y-axis, so let me write it as on minus hi by di. So if I equate the both equations, I am going to obtain the resultant equation in terms of small f, small d naught and small di. So this is my thin lens equation. Now I think you have got a clear viewpoint on this thin lens equation. And next, so any object, okay, any 3D object which satisfies here the thin lens equation will be lying in focus. So the thin lens equation, if any of the object is satisfying, means that object will be focused on your image plane properly, assuming that this d naught, okay, this d naught is very greater than this small f. Okay, that means the distance between your object and the lens of your camera is very far when compared to the distance between your focal point to your lens of the camera. Okay, there exists a terminology called magnification. So what is they will be asking you, what will be the magnification your lens of your camera is performing? So the magnification is defined as the ratio of hi by h naught. That means height of the object in the image plane to the height of the object in the 3D environment. Otherwise, in some other way, I can also define my magnification of a camera in terms of distances. That is, it is the ratio of the distance between the image plane to the lens to the distance between the lens to object. So this will be minus. It is a reversal. So whatever the thing I am seeing in my image plane are the real images for which my m will be negative. But for the virtual images, this m magnification will be positive. I will explain you the concept of the virtual images in further slides. So let me look over a problem here. So I am having a pinhole camera of length 12 centimeters. So that means 12 centimeters is the length of the camera that I was being given, used to photograph an object which is 60 centimeters away. So 60 centimeters means it is actually a d naught from the hole. Okay, and this object is of 70 centimeters high. That means h naught of the object is 70 centimeters. Okay, now calculate the height of the image in the image plane. So this is the question was being asked. So magnification is nothing but here the length of the camera by the distance of object from the pinhole. So that means, can I say this is my length of the camera, di. So di magnification is nothing but minus di by d naught. Of course, it is the distance between the lens of the camera to image plane, means it is indirectly giving me an inference that it is treated as a length of the camera, right? So m equal to minus di by d naught. So di by d naught here, which is the one 12 centimeters, the di is given, d naught is 60 centimeters. I can produce the value of my magnification as 0.2. So what is my objective that is asked in the question? The height of the image in the image plane. So height of the image by height of the object is also a magnification. So finally height of the image is nothing but magnification into height of the object. The height of the object given is 70 centimeter. So finally I am going to obtain the height of the image in the image plane as 14 centimeters. So this is the height of the image. If x comma y comma z is a scene coordinate and f x by z, f y by z is a pixel coordinate. So to get an image coordinate from the scene coordinate, that is a 3-dimensional to 2-dimensional conversion, what I am doing here, I am dividing the scene coordinate with its lost coordinate so that I will be getting here an image coordinate. So doing like this, that means dividing by z is a non-linear transformation. So what I will be doing to make it linear, I will add one more coordinate as shown here. So it is my pixel coordinate that is present on the image, and it is my scene coordinate in my environment. Okay, so I am going to add one more coordinate to make into a linear format. So x comma y comma 1. One more coordinate I have added here. In the similar manner for the scene also, let me add one more coordinate x, y, z 1. So this ultimately results me it is my homogeneous image coordinate and this is my homogeneous scene coordinate. So anyhow I have got an homogeneous formats for the image as well as for the scene points. Now I can also do the reverse conversion. Like if this is my homogeneous coordinates, this is my image and for this one is my scene. If I want to get into a normal coordinate form, I just divide this third coordinate with the first two. I just divide the first two coordinates with the third coordinate like this. That is x by w and y by w. Here also x by w, y by w and z by w. This is how I will be getting into normal coordinates. Now we have to study what is the perspective projection camera model. So here what is happening? The camera that is placed here, let me assume this is my lens of a camera. So that means it is my camera's optical center. Now the camera is looking along the z-axis such that the focal point of the camera is at the origin. Okay. So this is my focal point or the principal point. Now the image plane, this image plane is parallel to my xy plane. So this is my xy plane and this is my image plane which is at a distance of d units from the center of projection. So this is my optical center, right? Of course where the lens of a camera is placed here. So from here to this image plane I am having a distance that is small d units. That is, the perspective projection is nothing but it is the projection model that avoids the inversion where the center of projection is at a origin and the image plane, that means this is nothing but it is the projection plane, that means it is a plane of projection which is placed in front of the center of projection to avoid inverted image concept. So in my earlier cases of tin lens equation or pinhole camera model, what the image plane was present behind the lens of the camera, but here the image plane is present in front of the lens of the camera in order to avoid the inverted concept. Now, right, and this capital P is nothing but some scene coordinate and this small p with x and y as its coordinate is giving me the information of a pixel coordinate in the image plane, right? Now what is this virtual image plane concept? So in the inverted image concept, the mathematics were very difficult and it is intuition is also very difficult. So if I use the virtual image plane concept, it is giving me easy way to think the upright scene producing an upright image. So this is my scene. If the scene, whatever the scene that I am visualizing, the same can be reproduced on this image plane. Okay, so we will often use the virtual image. That means if this is my virtual plane, means inside it I will be having my virtual image. So this plane I will be using for my calculations. Now the geometry is essentially the same, like how we have taken in the case of a pinhole camera, like all the constraints, all the geometries like similar triangles or whatever, all the things are same. Only the thing is the sign will become reverse. Okay, how the sign is becoming reverse I will explain you. So the same perspective principle concept, perspective camera projection concept I have also explained you, explaining you by taking an object here. So a person is running, this is my camera center of the lens, camera lens here. The distance between the center of projection to your virtual image plane is small f, and this is my object, a point on the object having the coordinates xs, ys and zs. S represents it is a scene coordinate. and these coordinates, whenever they are projected on your image plane, they turn immediately into small xi, small yi, and this f represents, it is the distance between your camera center to your image plane. So these equations we got from the concept of similar triangles, hence I have reproduced it here. Now, as I have said you that my camera is looking along the z axis. So my camera is looking along the z axis, and I am having an object at x comma y comma z location, and this is my center of projection, this is my plane of projection, and it will be my image plane. So using the pinhole camera concept, so according to the similar triangles, the point x comma y comma z, which is a scene coordinate, is mapped into your image plane such that I am going to get finally the coordinates for the image plane as minus dx by z comma minus dy by z. So how I am going to get here? As the camera is looking down the negative real z axis. Okay, down the negative z axis, and from the similar triangles I will be getting. So if this is my scene coordinate, my pixel coordinate finally I am going to get ultimately in this manner. So this is the thing that is obtained from the similar triangles. So why it is minus d means, I have said you that everything will be same except the geometry will take its sign in the reverse way. So in the time of pinhole camera concept, I have taken as positive, but here I will be getting as negative because it is seeing towards the negative z axis, right? So, and here also, what is the size of the image formed by the process of projection is giving me, because you know the concept of similar triangles here, as ys is nothing but y by z into small d, because if you take this coordinate, so this is my scene coordinate, this is my pixel coordinate. Okay, so this is my image plane or plane of projection. That means I just replicated this diagram here. Okay, so if this is my positive d, okay, so that means it is considered, this point E is nothing but it is the center of projection. So from here I am looking towards negative z axis. So that means I am making myself d units far away towards the negative z axis, means from the law of similar triangles, this ys is given by y by z into minus d. So the same thing have happened here. Okay. Similarly, I will be also getting for x, and so finally I am going to ignore the third coordinate, as I am considering here the coordinates only for the image space itself. So I will be finally getting two coordinates for the image plane. So this is the concept of perspective projection, where the distance object appears smaller in the projection plane, because you see here, so this is my distance object and this is my lens of the camera. In the projection plane, what is happening? This object is becoming smaller, and here also this object is becoming smaller in the projection plane. Okay, so this distance object is appearing very smaller to me, and if this person, 3-4 persons are standing in this scene, the person who is more away from me, that means more away from my eyesight, he will be definitely appearing as a smaller person when compared to the person who is standing right in front of me. So this is the concept of my projection plane of the perspective projection camera model. So the projection process now can also be represented by this matrix equation. So xyz1 is nothing but what here? It is the scene coordinate which is in homogeneous nature. Why? Because I am having one more extra coordinate. Whenever the scene coordinate is multiplied with your transformation matrix of your projection perspective transformation matrix, I am going to get my image coordinate. So anyhow, I have taken, if it is my homogeneous scene coordinate, I will be getting my homogeneous pixel coordinate, right? So this is my entirely a homogeneous form. So x and y are divided by third coordinate here to get into a normal pixel coordinate. So ignoring the third coordinate to get the image coordinate, that is u comma v. So the same equation, the same expression is repeated here. That means here I am just dividing this third coordinate of the image to get, because this is my homogeneous pixel coordinate. If I want to get in a normal form, means definitely I need to divide with the third coordinate, the first two coordinates. So minus dx by z, this is minus dy by z, and this is u comma v. In this way I am going to obtain the pixel coordinates. Suppose, as I have said you, that this is the perspective projection matrix. So this projection matrix, if it is scaled by factor c, what is it inferring me? So this projection matrix, if it is scaled by a factor c, means the x comma y comma z is also scaled by c. This xyz is nothing but it is the coordinate of the object. It is a scene coordinate, a point. It is a point on the object which is present in 3D environment. So if the projection matrix is scaled by c, that means I am scaling x, I am scaling y, as well as I am scaling z also. Then can I now tell you that the size of the object increases? That means the object which appeared earlier to me, if I am scaling it up by c units, means every dimension of this object, like it may be a length, width or height, it also scales up. That means if length, okay, it is length and width, they are scaling up, good. Then z represents, it is nothing but the distance, like the separation between the image plane to your 3D environment. That means this object is moving still farther away from the perspective virtual image plane or plane of projection. So then we get a larger object is appeared here, which got moved away further from the camera. The same from the camera or from the eye. So but in image it results in the same view as that of a smaller object which was located nearer to the camera. So even though it is scaled, the projection matrix is scaled, the object got moved and its physical attributes got increased. But still the appearance of this object was same as the of the previous case, which was not scaled before. Okay, so the same view it is getting. So this is the concept of perspective projection matrix. Okay, so what the next camera model is? So the next camera model is nothing but it is the orthographic projection camera model. So in the case of orthographic projection case, what is happening? The distance from the center of projection to image plane is infinite. So as if it is the center of projection or the camera lens is placed here. So previously, in the previous case, the distance from the image plane, that means a virtual image plane to your center of the projection, is of finite quantity. But here the distance is moved towards infinity. That means more amount of distance. Okay, it is very farther away from the origin. As well as if the object is very much distance away from the origin or away from the lens, that means z tends to minus infinity. As I have said you that I am looking down towards the negative z axis, that means z is approaching towards the minus infinity, right? So what the ratio of d by z will become? So it will become minus d by z will tends to 1 here. So why I am stressing out here minus d by z? Because this d by z is obtained from here, right? Because this is my d by z, right? this is d by z into small y, this is d by z into small x. So this d by z is nothing but d by z into x is entirely giving me pixel x coordinate. This d by z into y is giving me the pixel y coordinate. This is small x, this x, this y are nothing but these are the scene coordinates of x and y. So minus dx by z is minus d by z into x is giving me the pixel x coordinate, minus d by z into y giving me the pixel y coordinate. So that is why it is ultimately tends to unity. That is a 3D scene, that means this 3D scene P and Q is a 3D scene or a 3D points is at infinite distance from the camera. That is what is depicted here. Now all the projection lines will become parallel to the optical axis of your camera. So if this is my center of the lens, so through the center of the lens only I will be having my optical axis, of course. So what is happening in the earlier cases of perspective projection, the rays are not parallel, okay, because this object is appearing in the image plane as a scaled down object. But coming to here in the orthographic or the parallel projection, the 3D scene is at infinite distance from the camera and all the projection lines are now parallel to the optical axis. Why? Because the image plane is far away as well as the objects are also far away. Therefore, the point, it may be a P or it may be a Q having coordinates values as x comma y comma z, they are directly mapped as x comma y comma z, as x comma y. Okay, hence the third coordinate is ignored. Hence it is called an orthographic or parallel projection. That means here can I say that this scene coordinate x comma y comma z is mapped into x comma y in the image plane. That means a 3D to 2D projection is happening, right? So how the projection matrix will be now, we will see. So this will be the projection matrix, because here the third term is ignored as something by infinity tends to 0. The projection matrix for the orthographic projection is something by infinity is tending to 0. So previously in the case of my perspective projection, there will be a value here at this location. So what is the value? It is minus 1 by d. But here as d tends to infinity, so this value will become 0. So this is my projection matrix for your orthographic projection, and this is my homogeneous scene coordinate, and this is my homogeneous pixel coordinate which is in the plane of projection of your orthographic view. Finally, if I would like to get into a normal pixel coordinate form, I will be dividing the third coordinate with the first coordinate, and the second coordinate will be getting divided with the third coordinate. I am going to get xy as the original or the normal pixel values of in the image plane. So let me have a quick differentiate out the perspective versus the orthographic projections. In orthographic projections here, the focal point is at infinity, right? Because the focal point is very infinity, you can see here, and the rays are parallel and orthogonal to image plane, because this is my image plane and these rays are orthogonal to image plane, okay, from the object. Okay, then the mapping will be like x comma y comma z are converted into here as x comma y. But coming to the perspective projection, the x comma y comma z will be converted into some minus d by z into x or minus d by z into y, right? Because you have already observed minus d by z into x and minus d by z into y. Those will be your pixel coordinate, but here directly you will be getting x and y as its image coordinate, pixel image coordinate. But the main thing here you need to observe here is Jet information you are missing in the orthographic view. So this is the difference of your perspective projection with your orthographic projection. That means in the orthographic projection, the projection rays are very parallel to x-axis, but here when coming to your perspective projection, the projection rays are approaching towards the origin in decreasing the inclination. Okay, in declination way they are approaching towards the origin. That means the object will be scaled down in the image plane, but here the object will be appeared as it is, how it was in the real scene. The same thing also have been depicted. This is the perspective projection view and this is my orthographic projection view. Okay, there is a concept called vanishing point. So what is this vanishing point? So in our day-to-day life, you people might have encountered with this scenario, but you don't know what exactly this is. So I am having my center of projection here. This is my image plane. At infinity, I am having a point P. If I see projection of this point in the image plane, it got appeared at V. This point I am going to call it as a vanishing point. This is my vanishing point. That means I have some 3 points. Let it be A point, B point and C point on the ground plane. So correspondingly for these 3 points there will be a projection in the image plane. So let it be a small a small b and small c will be the projections of capital A and capital B, capital C on the image plane. If suppose if the points of A, B and C are moved away like this in this manner, are moving towards right side and they are moving still towards right side and approaching towards the infinity, then the projection of the point in the image plane, what it happens, so C is moving like this, B is also moving like this, A is also moving like this. That means can I say now this small c, small b, small a, which are the projections of these original capital A, B, C, will move towards this V. That means a vanishing point. Finally, the projection of a point at infinity on the image plane is nothing but a vanishing point. That means as these points are moving, these 3 points are moving towards this V point. Okay, this is the concept of the vanishing point. So how to explain this vanishing point concept in other way is, if on the ground plane 2 lines will be running parallelly like this, this is one line, this is one line, these 2 lines are running parallelly to each other. Of course they are the tracks, railway tracks, but there will be a vanishing point. So this point I am going to call it is a vanishing point. So what is this vanishing point here means? So at infinity the projection of this point in the image, because of course there is some object or something will be there here at this object, okay, at this 3D environment. So the 3D environment, if it is projected, let it be my image plane. So this point, this image point, I will be getting one image point and this image point is nothing but it is a vanishing point. So that means the ray from the center of projection rho V is parallel to the ground lines, as this is I have considered one ground line and this is one ground line. So the best example for the vanishing points are railway tracks, where or the road this way, like this is also a best example I can give, where a person will be standing in between or at the center of the road or at the center of the parallel tracks, and he will be having vanishing point at the center of this image plane. Okay, so this is my vanishing point here, and the same thing vanishing point can also be observed here. Coming to this figure, in the figure there will be some parallel lines L1, L2, that means this L1 is approaching towards this point, this L2 is moving towards this point, and this L3 track or the parallel line is having the other end at, it is meeting at this end, or it is not actually meeting. The appearance wise it is perceiving or giving an impression that these 3 points are meeting here, and similarly these two tracks are meeting at this point, and similarly these two edges of the road are meeting at this point. This is the perception what we generally get, but actually and truly speaking they are not at all meeting, right? So parallel, this L1, L2, L3, these parallel lines are running parallelly to each other or on the same plane. Similarly, L4, L5, L6, these three lines will run parallelly each other. So if I stand at L5, I will be facing my vanishing point here at V1, and if I stand on L2 line, I will be facing my vanishing point at V2, right? So these V1 and V2 are nothing but a collinear vanishing points, and the line which joining these collinear vanishing points is nothing but it is the horizontal vanishing line. So this is the concept of perspective camera projection, orthographic camera projection, and pinhole camera and vanishing point. So let me end for the day. Thank you and have a nice day.